In this week's lectures, we're going to turn back from looking at finite length signals to looking at infinite length signals and coming up with a Fourier transform that is matched to this case. And it turns out the transform of choice is called the discrete time Fourier transform, or DTFT. So the DTFT is the transform of choice when you're trying to do Fourier or frequency analysis of infinite length signals and systems. An important tool. It is extremely useful for conceptual and pencil and paper work, design analysis. However, since it's set up for analyzing infinitely long signals, it's not really a MATLAB friendly tool. And so most of our work will be of the pencil and paper variety, and we'll leave MATLABing to the DFT. Speaking of the DFT, the properties of the discrete time Fourier transform are very similar to those of the DFT, and so we'll be able to go quite quickly through them. But there are a few gotchas, a few tricky spots that we need to beware of. And the way that we're going to derive the DTFT is as a certain limit of the DFT, and that's why the properties are similar. Basically, we're going to think of what happens to the DFT as we let the signal length be finite, so that the DFT makes sense, but get longer and longer and longer. And we're going to see that you can define the DTFT as the result of this limiting process. So just before we jump into that argument, let's just recall the DFT. And for this lecture, we're going to focus on the unnormalized version of the DFT. And just remember, it has a analysis formula. And in the analysis, what we're doing is we are computing coefficients xk that measure the frequency content of the signal x at the frequency k. And they do that through this inner product between the signal and a harmonic sine wave basis function at frequency k. This inner product, it basically measures the similarity between the signal and that particular sine wave. And so these are the coefficients that you want to use in the synthesis formula in order to build up the signal x from a linear combination of sine wave basis functions. So let's just remember the DFT, very useful, applies for a signal of length n. And now what we're going to do is we're going to start playing some games around letting n become longer and longer. But before we do that, we're gonna first play a game around the sum, and we're going to rewrite this sum instead of from n equals 0 to n minus 1. We're going to write it from minus n over 2 up to n over 2 minus a half, much like we did frequently with the DFT last week. So we're going to just give this a name, the centered DFT, just for fun. And we just remember that since the DFT is interpretable as a periodic function with period n, we don't have to index x with k's that run from 0 to n minus 1. We can also index both the time signal, time n, and the Fourier transform, xk, using indices that run from minus n over 2 up to n over 2 minus 1. And it's very important to note that the length of this interval is n samples. And that means since the length of this interval is the period, we capture all of the information in both the signal and its DFT. So we're going to use a set of modified forward and inverse DFT formulas that are given here. They look just like the regular unnormalized DFT, except that we're summing now from minus n over 2 to n over 2 minus 1 in both cases. and we're interested in the indices k, frequencies k, and times n similarly over these time intervals from time and frequency intervals from minus n over 2 to n over 2 minus 1. And this is what we're gonna think of as the centered DFT. The last thing I want to remind us of is that when we're computing any DFT, the frequencies have once we pick a value k, that defines a frequency omega k, which is just 2 pi over n times k. And no matter how large n is, it's very important, no matter how large n is, the frequency omega k always lives between the frequency minus pi and the frequency plus pi. And that's because no matter how large k is, we're only indexing, or rather, no matter how large n is, we're only indexing k between minus n over 2 and plus n over 2 minus 1, which if you just plug in n over 2 in here, you see the n's cancel, the 2's cancel, and you basically get minus pi. And so it's very important that no matter how many points there are in your in this particular DFT, we're always in a situation where the last point corresponding to k equals minus n over 2 corresponds to exactly a frequency omega k equals minus pi. And the point, the very last point on this side corresponds to a frequency just below frequency of plus pi. And that doesn't matter whether n is 4 or whether n is 4 million. When you have this representation, you're always bound between these frequencies minus pi and plus pi. And so now what we're going to do is we're going to play a game where we're going to let n these sum bounds go towards plus infinity and minus infinity, and we're going to see what happens as these bounds go to plus infinity and minus infinity, but we're still stuck inside this interval minus pi to plus pi. So we're going to take things to the limit. You can hear the strings rising up in the background. What we're going to do is we're going to start with the forward DFT formula, and we're going to let n increase towards infinity. Okay, and two things are going to happen, right? The first thing that's going to happen is these sum bounds are going to become plus infinity and minus infinity. That's easy. So we're going to be looking at an infinitely long signal. That's really easy. The second thing that's more subtle is what happens in here with the frequency omega k. Because recall what we just talked about in the previous slide, that no matter how large n gets, no matter how close it gets tending towards infinity, we're going to be sweeping over an ever larger range k, and therefore the frequency omega k, defined as 2 pi over n times k, is always going to be stuck between, again, minus pi and plus pi. And let's just look at a numerical example of what happens, and it'll be really clear how we move from the DFT to the DTFT. So what I've plotted here is on the left a time signal that are the exact same samples of my time signal, but I'm basically letting it expand. I'm taking this same 32 sample central portion that you see is reproduced here, that is again reproduced here, that is again reproduced here, and I'm basically allowing the signal to grow. And in this case, I'm padding it with zeros, but you could actually even have signal fluctuations out here. Nothing would change. So I'm allowing the total signal length n to grow from 32 to 64 to 128 to 256. It's doubling every time. Now let's look at what happens to our DFTs. Very interesting thing happens to the DFTs. The time signal, you can see, is getting squished in. But the DFT does get squished in a different way, because remember, no matter how many samples there are n in my in my DFT, I'm always limited between the frequency minus pi on this side. I'm pinned to that frequency, and plus pi on this side, right? Always. And so basically what you see is, unlike the case here, where there's additional degrees of freedom outside of the signal in the time domain, what happens in the frequency domain is samples start filling up the interstitial space between samples. Basically, we're interpolating between samples. Basically, we have 32 samples in the interval minus pi to pi, and then we have 64, and then we have 128, and then we have 256 samples. And it should be sort of abundantly clear that as this process goes with n going towards infinity, that basically this is going to no longer be a set of samples, but it's actually going to be a curve, right? A function of a continuous variable. That basically the frequency omega k, which equals 2 pi over n times k, is basically going to converge just to a real valued variable omega that lives between the values minus pi and plus pi. And that's exactly what happens by this limiting process. Making the time signal longer interpolates or provides more information between the samples, and in the limit you basically map out a function of now not a discrete variable like everything has been in the course up to now, but a function of a continuous variable. And we're going to call this function of a continuous variable the DTFT. Okay, and it plays a role just like the DFT, but instead of having a discrete index, it has a continuous index. So this limiting process, as we've just talked about, letting n go towards infinity, naturally will give us an infinite sum. And moreover, the frequency, the fact that the frequencies are becoming closer and closer together, will naturally push us towards a frequency omega that is a real number and ranges in the range minus pi to plus pi. And we're going to call this formula the forward or the analysis discrete time Fourier transform, or DTFT. The nice thing about this formula is it behaves really just like the forward or the analysis DFT. We have the same interpretation. We just have to be comfortable with thinking about signals as vectors in infinite dimensional spaces. But let's just we can see that we can interpret this value x of omega, which equals this formula here. This is nothing other than an inner product, right? This is an inner product between two signals, right? Recall that the inner product for infinitely long signals is an infinitely long signal x and an infinitely long signal y is just the infinite sum of their dot product, basically the product of the two signals taken pointwise, where we conjugate the second signal. And so you can see that this is nothing other than an inner product between the signal x and kind of abusing some notation, a signal e to the j omega n, right, which is a sine wave. It's no longer one of these harmonic sine waves that it has a frequency that's a ratio of some factor n times 2 pi. It's basically any real valued frequency. Okay, and so it's basically just an extension of the DFT to move beyond harmonic sine waves to arbitrary sine waves. And so we have the exact same interpretation of the value of the DFT at frequency omega. It basically measures the similarity of our signal xn to an infinite length sine wave e to the j omega n via this inner product. Right, so just like the DFT. So the derivation of the forward or the analysis DTFT is straightforward. The analysis, the derivation in the limiting process of the inverse or the synthesis DTFT is a little bit more subtle, and so we're going to be a bit more hand wavy about it. But it also makes some good sense. So let's rewrite or just recall the centered inverse DFT formula that we introduced a few slides ago. Basically, it's just the usual inverse DFT, except now the index is between k equals minus n over 2 and k equals n over 2 minus 1. We have a 1 over n factor in front, and let's just introduce a 2 pi over 2 pi, which doesn't change anything. So now if you just stare at this formula for a little bit, and you think what happens as n goes to infinity, you see some interesting things happen. Well, first, from the forward formulation, we already know that these harmonic sine waves are basically going to become arbitrary infinite length sine waves. So the frequency 2 pi over n times k is just going to become a arbitrary real valued frequency omega. Secondly, the DFT is going to become the DTFT. That's already introduced in the previous slide. More interesting, or more sort of new, we can think of this quantity 2 pi over n is basically becoming like a quantity d omega, a little bit of omega, because you can think of it as appearing over here, and it also appears here in this formula. So you can think of 2 pi over n as a little bit of omega. And finally, this combined with this little bit of omega combined with this term, sum term going from minus infinity to plus infinity, you can see, if you're familiar with calculus and Riemann integrals, for example, that this is looking a lot like, in a hand-wavy way, a Riemann integral, where the sum becomes an integral over minus pi to plus pi, and the 2 pi over n becomes a d omega. And that allows us to introduce the inverse DTFT formula, or the synthesis formula, which is a little bit different than anything we've seen up to now. Now there's calculus. Now we're building up our signal x of n. We're still building it up out of a set of sine waves of different frequencies omega, and these sine waves are weighted by coefficients capital X of omega, but now there aren't just n of them, there are infinitely many of them. And the way that we represent a sum over infinitely many sine waves, where they're indexed by a frequency that's truly a not discrete at all, but a continuously varying value, is by using an integral notation rather than a sum notation. Of course, there's no difference between an integral and a limit of sums, but this is the standard notation for writing this. And then we see this extra 2 pi that we introduced over here becomes a nice normalization factor here to take us from d of omega, which is in units radians per sample, divided by radians, takes us just to units of samples, which is the units of time over here. And of course, now we can evaluate this integral for any value of n in the interval minus infinity to plus infinity. So this is the forward and inverse DTFT. So just to summarize, we have these very interesting and intriguing formulas that seem a little bit harder to get our head around than the DFT, but they still make quite a bit of sense. We have a synthesis formula that tells us how to build up a signal x as an infinite sum of sine waves that are weighted by coefficients x of omega. How do we get the coefficients of x of omega? Well, we use the analysis formula, and we set the size of the coefficient x of omega by the inner product between the signal x and this, call it, if you will, a basis function, although it's basis function in quotes, that is a sine wave at the frequency of omega. So the interpretation of analysis and synthesis is completely the same as in the DFT. Now, though, we just have to deal with infinite sums and this integral. We saw that we derived this set of equations by thinking of the DFT and taking it to the limit as n goes to infinity. And as we just spoke about, this analysis, synthesis, interpretation holds equally well just as it did in the DFT. In the next lecture, we're going to see how this DTFT idea can be applied to study Toeplitz matrices and linear time invariant systems in the infinite signal length case, and we'll see that we can do a eigenanalysis that's completely analogous to what we did in the DFT and the circular convolution case. So we'll see you in that lecture.